strong Roman concrete,
fully hydraulic,
structural solid connections.
It's the
structural
Engineering podcast.
Hello, welcome to this week's episode of the Structural Engineering Podcast. My name is Max.
And I'm Zach.
This week we've got a sequel for you, and if there's anything I know about sequels, it's they're always better than the first one.
And they're always windy.
And they're always windy. This is the Too Fast and Too Furious of wind. But before we get into wind, round two, let's do a tip of the day, huh?
All right, what do you got for us, Max?
This is a real quick one. This is something I've seen on general notes forever and ever, and I never really knew why, and I just went with it. But I figured it was time to look it up. This is, don't put aluminum in concrete. Never, ever. No conduit. That's usually the case where you'll get it. Makes sense, right? But so aluminum and concrete will create hydrogen gas, apparently, which is explosive, I guess. And corrosive. So I read a story before people totally got that figured out. And this wasn't that long ago. A cement mixer company said, "Oh, I bet we can make a much cooler cement mixer if it's aluminum." So they built this, giant drum and poured concrete in it, mixing it around, and bottom of it exploded off because it filled with gas.
No way.
This happens with wet concrete, and it happens with cured concrete as well. I found a really cool article, and they just gave some fun examples of, using aluminum rebar ties back in the, I don't know what this was, 50s or something. And this building just kind of started to crumble, and you could whack with a hammer, and everywhere that it would crumble, you would just come right to a rebar tie. So
wow,
it's bad.
So you're not even supposed to put it. So you're saying don't encase aluminum in concrete, but what if you put aluminum up against concrete?
Don't even touch it.
Wow. Okay.
Rub it up there.
Huh. Interesting.
Yeah.
Well, that's a good tip. I got the news this week for you, Max. It's always a sore subject, a little bit of talk about failures, but I think it's something we always need to talk about because you learn the most from failures than anything else. And this one's about that bridge in Florida that collapsed.
Oh, yeah.
Pedestrian bridge that collapsed during construction. Pretty big cracks. I believe they're up to 1/4 to 3/8 of an inch. So pretty good size cracks. And the engineer got called out on site to take a look, and they had tons of meetings. And the engineering firm said, "Oh, it's okay. We expect it. We ran through our calcs. Don't worry about it. It's all good." And then it failed and unfortunately killed some people. And very tragic story, no doubt. But I think I think this story is such a good example to learn off of. It's amazing. So first of all, in general, if your concrete's cracking over 1/4 of an inch, that's a big deal. I don't know when it wouldn't be a big deal, right? Like something's actually happening there. You're not getting like cracking due to temperature or shrinkage or
it's cracks. Yeah, its cracks are usually pretty evident. If it's not hairline cracks, from stress points or something, worth looking into.
Right, 1/4, 3/8 of an inch. I mean, that's a good sized crack. And so what they ended up finding was that it was a modeling error in the software they used to model the bridge.
No way.
So when they told them it was okay, they looked at everything and they said that the demand was much, much, much lower than the capacity, so it should never crack. Well, it actually turned out that was completely wrong, and they undersized, that whole area. And preliminary, they haven't came out with the full report, but it ended up being that issue that failed it. And the way my understanding, and this might be wrong, we might correct it over the next few episodes as we've learned more, or maybe longer, but it was how they were inducing post-tensioning on the structure caused more of this to happen quicker. The other thing is, and I think this is something that's pretty interesting and makes so much sense, is like in a structure, we go beam to girder to column to foundation. There's a very strict load path and we're good. And we don't really think much about redundancy. That is something in bridge design that's like a 101 thing. Like your bridge, you should have redundancy. And the bridge in Florida had one center truss. So if any part of that failed, the whole bridge collapsed. And so that's a reason why most bridges have a truss on each side of the roadway. Is it's a little bit of redundancy, and there's a lot more to it than just this one main span truss down the center that if something happens, it fails. So I think it's something to learn from is both, redundancy. You should definitely think about it, especially in a structure like that.
Absolutely. That's applied to bridges and everything else that you might do.
I think to me, the biggest takeaway from this is the modeling error.
Yeah. The gut check, the quick hand calc to maybe tell you how close you are.
Yeah, exactly. A little bit of a tip, a little bit of a story, a little bit of some news.
Now let's talk about some wind. Do it. We were talking earlier before getting on the mics, and this was a hard one for me, I think. It's seemed like such a simple, I've applied a wind load to hundreds of buildings, I guess. And the one that you're taught to use by your first, PM, you get the technique in your head and you roll, and it's not all that complicated, but there's kind of a lot going on here.
Man, when you get diving into wind code and where it came from and how it was developed, and then you go into all the nuances of each type of loading you can do, and it gets so confusing so quickly.
Yeah, and we'll get into it, but I think it's just preposterous that there are 4 ways to get a main force resisting system on one type of building with 4 different answers, which can be dramatically different.
Right. And I think as I'm diving into this, I don't know how much I'll change what I'm doing, but it definitely makes me think a lot.
Yeah, I don't know. Let's get into it, and we'll reflect. When it's time to reflect. Let's talk about where these things come from history-wise, because I think they have some cool developments. And I guess we'll say, I followed most of the directional procedure, and Zach was following along with the envelope procedure. So this is a little bit of a directional versus envelope. All right, so let's go back in time. This is how old, 1972. This is how old the directional procedure is. This is, what led into ASCE 7. It was ANSI standards then. But even before that, it kind of came from Metal Building Association. I think we talked about this in Wind episode 1. But really the first institution to care about wind loading, and probably because they're so light, was the Metal Building Manufacturers Association. They're a key player in sponsoring research that has led to the understanding and codification of wind loads. And that was really kind of where, the start of the directional method. What do you got for envelope?
Actually, interesting. Envelope started in 1974. Research began through UWO and
Ontario.
Yeah. And, that research stretched out for quite a while. They had different phases and looked at different various buildings and wind tunnels and modeling, and really just started trying to evaluate the influences of different parameters on wind loading.
Yeah, and I believe, and this might be a little bit off, is the directional procedure was, not perfectly accurate since it was designed around a very specific building sort of dimension, this metal building. It might have been ASCE was looking for additional research to kind of, build up on what was already there. And so they looked at Colorado State and UWO, and UWO won this, and they went ahead and developed some of the envelope procedure. But later on, this is what I like to do, the directional method, ASC went back to CSU and talked to a professor there and helped kind of improve the directional method a little bit, or continue some of the research there.
I think that's pretty awesome.
Yeah. So these things have been around for a super long time, but they seem to have some problems. There are 2 totally independent systems. Some of the preliminary tests, the reasons they had to jump forward. So the MBMA sponsor test, the metal building, didn't account for boundary layers. This is, slowing at the ground level, basically. This is, as I imagine it, kind of just a building in space, which is not really what we're dealing with. But yeah, later on, the wind tunnel at CSU and Ontario were the 2 leading wind tunnels in the North America, at least, that could consider boundary layer effects. So they took it on, and the rest is history.
Now, before we dive into this, with all your research, which one are you more of a fan of? What do you think you would back?
Well, I'm on team directional, and I'm going to argue it till the end. But
Awesome.
Swayed, and I might be swayed, to be honest. I wish they were more consistent. I don't know. Directional is certainly easier, but that's not a good excuse.
What do you use on a day-to-day basis?
Directional. And I think almost everybody, that's what they use. I don't want to, paint with broad strokes here, but the few, let's say, 4 firms I've worked with, pretty much directional across the board.
Yeah, I'm there with you. That's why it's okay. You know, to be really honest with you, I wish, I understand this is not feasible. More or less, I wish all my buildings could be wind tunnel tested.
Personal wind tunnels.
Yeah, I mean, why not? I understand that, analysis of this computer-wise is very difficult, not very feasible at this point in time. Little office wind tunnel, that'd be pretty cool.
Sure would.
I mean, I got one at my house right now.
We're waiting on the video too.
It's going to work soon. I promise.
Then you could start doing all your buildings. Yeah, I think I wish there was a little more rigorous of an analysis available just based on seeing how much these things can vary. We'll talk about an example later. But I mean, you could see huge swings, which makes me hesitant to believe one.
Yeah. Oh, yeah, absolutely.
Yeah.
And it's probably not the right approach to go with the one with the highest pressure.
Oh, yeah, definitely not. I think the idea in the code actually states is that the envelope procedure generally should result in lower pressures, right?
Right.
For a low-rise building specifically. I would think the simplified directional might give you the highest because it should be the easiest, and the directional down, and then, envelope on low-rise should give a nice low pressure and realistic, hopefully. This example that I'm seeing here is quite the opposite. So they just jump all over the place. I don't know.
Okay, so before we get into examples and whatnot, give us a little intro of directional procedure within ASCE 7. When can you use it, and what are the limitations?
That's a good idea. Okay, so it's for all heights. You can use it all the time. You can use it for pretty much every building, more or less. The simplified method limits your height to 160 and simple diaphragms. There are some conditions, a building that is a little bit special where you're not allowed to use it. And pulling this out of ASCE 7, if the building is not regular shaped. So that's a reference to section 26.2, which defines a regular shaped building as one that is regular shaped, more or less.
I love it. What a codified definition.
Yeah, it says there's just nothing really, to grab here. It's any building that doesn't have anything weird going on.
Which I thought was...
I should give you the real quote, but it's just about as good as that. Here we are. A building or structure having no unusual geometric irregularity. I mean, that's pretty close to using the word in its definition.
Absolutely. I get it in a code sense. You have to be so vague because it'd be very hard to define that, I would believe.
Yeah. So on top of that, we also have the building shouldn't have response characteristics, making it subject to a crosswind loading, vortex shedding, galloping, which I've never heard of, but flutter, which is the other version of that, channeling effects, or buffeting. So if anything weird is going on, maybe the building itself has a tunnel through it, and so you've got some channeling.
Right.
But actually, right next to that, where they say it can't have response characteristics, that might tee up with vortex shedding. The provisions of this chapter do take into consideration load magnification effect caused by gusts and resonance. So this is jumping to the worst case scenario, which is why you can take some reductions depending on the stiffness of your building. But this is assuming that your building is in sync with a 3-second gust, which is, there's only one little band of buildings that meet that, and low rise is probably not it. So right off the bat, I get the feeling from there that it should be more conservative. And what do you have? Envelope procedure.
Yeah, it's very similar to that. One thing I want to point out too about both of these, and it's something that they state in the code that I would say as a new engineer, I wouldn't have thought totally or questioned it, but is the idea of shielding. And it states right in the code, there shall be no reductions in velocity pressure due to apparent shielding from other buildings. And as a new engineer, you'd be like, well, why? It's there, right? I'm building up against a whole nother building, like it has to be. But the whole idea behind shielding is that building may be gone one day, and you can't rely on the building owner to be like, oh no, the building's gone, let's hire a structural engineer and reinforce the building. I really like shielding. I found in my career, this has come up probably a handful of times.
Really?
Yeah.
We know that another thing with shielding that I think is worth considering is that, we know from the last wind podcast that the forces that we're seeing on the building are not necessarily the same as the sum of the force on the front and the suction on the back. Those are pseudo forces developed to mimic the base shear found on the building. So, if you remove the back wall of a building, it's not necessarily just gone because that force was only added to make a similar base shear. So it's not quite the direct parallel. If you have a directly straight on wind line and you also have some shear on the side of the building, you're probably getting pretty close to what that would be without the suction on the back. So
envelope procedure, and I'll read a little bit from the code because it's not too much of a reason to
get creative with it. I think the code nailed it. They got it right. They got good words.
I think the words are pretty good. So it just like the other procedure you just talked about, it goes through building types, conditions, limitations. Building types are fairly similar. There's two parts of the envelope procedure. Part one applies to all low-rise buildings, and then it separates those loads into windward, leeward, sidewall, etc. There's a part two that applies to like a special class, let's say, not defined in chapter 26.2 of low-rise buildings that are designed as enclosed simple diaphragm buildings. But a simple diaphragm, something that's probably not cantilevered. So those are the type of buildings that you can use your envelope procedure in. Pretty much left you open to everything.
Yeah. But I gotta wonder, how many buildings have you done with mild cantilevers and not even thought about it?
All of them.
I know. Yeah, there's a couple provisions in here that we're the only two people that don't know. But I feel like they're neglected quite often.
Yeah, and I think it comes down to engineering judgment of what substantiates enough of a cantilever, let's say for this example, to not allow this. This kind of gets off this topic of envelope really quick, but I think there's so much engineering judgment that goes into a lot of this, and I think a reason why you're not seeing a lot of main wind force conversations is because we don't really often see, if at all, wind failing a structure, right? Maybe a little cracks here or there, or jip. Maybe it's more of a deflection thing, but it's not usually like a stress, right? It's a serviceability concern. A lot of the times, hurricanes and tornadoes, totally different story here, completely different story. And I think that's why in the last probably 10 years, to my knowledge, that components and cladding has become such a big deal is because there's more failures of components and cladding during a wind event than there is of a building.
Absolutely.
So I think a lot of these things are written in such a manner they're very vague.
Yeah. If I could see one example of a building failed, it doesn't happen. So let's go through, we'll jump back to directional and kind of go through the procedure a little bit. I don't want to be boring, but we'll just jump through it pretty fast. ASCE 7 in the beginning of each chapter actually gives you a step-by-step procedure to follow, but I figured I'd just go through, what type of results you'd expect to see, what the results are going to look like more or less. So going through the steps, and this matches with the first podcast a little bit. First, determine your risk category. In ASCE 710 and beyond, that's going to change what map you're in. 7.5 and under, that's going to change your importance factor. Then determine your basic wind speed. And then you've got all your parameters. Exposure category, topographic factor, gust effect factor. Okay, so then we're moving on to step 4, determine the velocity pressure exposure coefficient. I don't know why that's not in step 3, honestly. And the velocity pressure, QZ, QH. So these are the coefficients that you're going to use in your equation to modify this pressure for the face of the wall, internal pressure, and sides and back of the wall. So moving on to step 6, more coefficients, of course. And these adjust for the height of your roof, and rather the pitch of your roof, CP, CN. From what I've read, low-rise buildings are actually really sensitive to the pitch of the roof. And as the building gets taller, the sensitivity of the roof goes away, but instead it gets more sensitive to its proportions. So a tall, thin building is much, much different than a tall, wide building, not really proportional. These things really vary quite a lot in your building ratios. So if you go through the directional procedure, the all heights method, you'll end up with a pressure at the front of your wall, an internal pressure pushing back on the front of your wall, an internal pressure pushing backwards on your back wall, and a negative pressure. And you'll have a handful of these combinations. I know, sorry, that's a mouthful. But with every single thing you look at, you'll have 4. And the wall pressures, the internal wall pressures, are always going to cancel out if the building's symmetric. But your internal roof pressures are not necessarily going to cancel out. Maybe in the horizontal sense, but in the global overturning sense, they're not going to. So you'll kind of have 2 cases depending on your internal pressure, positive or negative, where your horizontal net will be the same. There's just 2 ways of looking at it. And there's another little piece of the directional procedure, which, again, I had completely forgotten about, which just is crazy. And this is the 4 cases that you have to run to make sure that you're covering your bases. It's not really going to be a big deal, I think, unless your building has some asymmetry to it. And this is what it's designed to pick up, I believe. But you need to be running your building with all of your pressure down one line, so front and back. Then you also have to do 75% of your pressure down one line and 15% skewed. And then you have 2 more cases very similar. 75 in a skew, or 75 times 75, 0.563, and 2 skews. So it's basically applying torsion to your building and making sure that your main wind force resisting system doesn't see a load that's higher than just that single linear case. Sorry, that was a lot.
I think we're tracking.
Yeah. But I could see in some cantilever cases or whatnot, where applying some torsional wind loads will get you higher shear wall loads than what you would get if you just apply 100% in each direction, totally separate.
Yeah, absolutely.
I guess actually this is So lead me through envelope a little bit.
Yeah, so I'd like to first start off and say the envelope procedure is 10 pages long.
Did you make it through?
I made it through. First thing, though, just to note a little bit, it talks about, there's a user note at the beginning of chapter 28, which is the envelope procedure for main wind force. And it says in there, for building shapes and heights for which these provisions are acceptable, this method, being the envelope procedure, yields the lower wind pressures of all the analytical methods specified in this standard. And with a little research I did, it said that's fairly right. You know, it's hard to give a blanket statement for everything, but in general, this is going to yield you your lowest pressures.
Interesting. I don't think that's true.
Yeah, so that's ASCE 7's
first lie.
Stand on it, and their belief of utilizing the envelope procedure. So just like yours, there's kind of a step-by-step of what you do, and we'll go over this, fairly quick because a lot of it matches what you do. There's only a couple things that are a little different. So again, step 1, you start with your risk category. Step 2, you get your wind speed, which you just call up your jurisdiction. They'll give you your wind speed. We kind of went over that in part 1 of our wind podcast. Then we kind of from there jump into, determining your wind parameters. We figure out the directionality factor, figure out the exposure category, which is, again, a little bit engineering judgment. A lot of cities, jurisdictions will have that for you. Topographic effects, all of these things we went over in the first wind design. And then you get your velocity, pressure, exposure coefficients, which we'll go over here. Then you determine your velocity pressures, and then you get this GC sub P to determine your external pressure coefficient.
Same as directional.
Yeah. So one thing that I don't like about envelope is it kind of pushes things together more, and I'm thinking we just only do high seismic and don't worry about wind, but whatever.
Yeah, you Washington engineers have it easy. All you got to worry about is a little earthquake. This is very confusing.
Yeah, like a little, they've made seismic code really straightforward. It just gets complex when your loads are really high, and then you have to go to doing crazy stuff to your building, but getting the load's not very hard. we jump into the code, we get our velocity, pressure. Now you can take your elevation effects, whatever. So the first part in here, 28.4, you get your design wind pressure for low rise. And then you go down to these tables to get the external pressure coefficient. Sorry.
No, that's right. I mean, the steps are almost the same. They really are the same. It's just different end result. And a little bit different limitations on what type of buildings you can look at.
Yes. And the way to get these factors are a lot more tabulized.
Yeah.
In the envelope procedure. You go through here, and to get your wall and roof loading, there's a simplified design wind pressure, and you can just pick a wind speed and pick a zone, and there's your pressure based off your roof angle.
Yeah. To be honest, I didn't get into simplified directional too much, but I know it's a fully tabulated sort of design. Same idea. So it's right. Very, very similar procedural wise, directional versus envelope, but drastically different numbers. I think maybe now's a good time to pull up this example. I found a pretty cool paper by a lot of people a lot smarter than us that really took a look at ASCE 710 and kind of critiqued its standard methods for determining wind loads. They had a couple different sections, but this is critiquing the analytical method for determining wind loads on main wind force resisting systems.
I read this same thing.
Did you?
Yeah.
They also said, and I will completely paraphrase and sort of make this up, but it's really here. Wow, I can't believe there are 4 different methods. They said it better than that, but really 4.
It's absolutely absurd.
Absurd. So
what standard do you go off of in anything that has 4 different options for you just to choose willy-nilly?
Yeah. So the example they have here, they said, consider a rectangular office building. It's 45 feet by 40 feet. It's 15 feet tall, and it has a roof pitch of 26 degrees and a mean roof height of 15. It doesn't sound like an office building. It sounds like a house, but that's all right. Going through the different methods, the envelope procedure, which generally is lower, it bills itself as being lower for low-rise buildings, was up to 60% higher wind forces than the directional procedures, both of them. That's dramatic. I mean,
it's huge.
That's 50% more shear wall. I feel like if you run into a case where you don't have enough shear wall, just run a different method.
Yeah, I think it'd be really interesting future podcasts from here. And I want to say this so that we kind of have to follow through almost with this. But I think as we interview professionals moving forward, we should ask them out of curiosity what wind method they use.
Yeah.
And maybe we're putting them on the spot and they don't actually know, but it'd be interesting to see.
Example, they had a couple like that and all very similar. Looking at CNC loading, which we're not really going to get into here, components and cladding, but they follow similar procedures. There's a directional version of components and cladding that stem from the same research. But like you're saying, there's a little more thought nowadays, I think, going into component cladding research, because that's where all the insurance claims come from. I think that kind of wraps it up for me. Are you swayed at all? Are you a directional guy or an envelope guy?
I'm wind tunnel all day, every day.
I'd like to think in, 20 years, maybe 10 years, computers will be advanced enough, fast enough that we can basically do these, complex models in no time at all. Just load in your Revit model and it'll tell you exactly what the base shear is and all the pressures.
It'll probably just be built right into Revit.
Yeah. That's right. Revit Robot and then Revit Windy Robot.
Yeah. Now, do you think something like that's needed in the industry?
No failures. I mean, what's the reasoning, I guess? I'm disappointed, I think, in the industry here, but there's no failures. What are you going to do?
Absolutely. I think that's a good point and a good place to kind of leave this. I want to expand on something I just learned recently, which I think is one of the coolest things ever. We just posted about this on our Instagram page. We were talking about the Vista Tower in Chicago.
Oh, yeah.
I think this tower to me, explains the use and the reason for wind tunnel testing buildings.
Oh, yeah.
to explain the building a little bit, it's about 1,200 feet tall. It's 80 feet wide, and it has a lot of nuances to it. Every single floor changes in geometry a little bit. So all the perimeter columns are sloped in some magnitude. Wow. So they did wind tunnel testing. This is right on the lake, right on the Chicago River. It's getting, big wind loads. The way it's directed is, from my understanding, is the wind's kind of coming at it at an angle. It's not straight on to one face or the other. I think a skyscraper definitely triggers that non-ordinary structure. What do you think?
Oh, yeah. Yeah.
I mean, we didn't bring this up, but the extents of the envelope method, which was chapter 28 that I spoke about, really applies to buildings with like a mean roof height equal to or less than 60 feet. I mean, all of a sudden you get to 1,200 feet. What the heck is the wind doing there? How does that affect that change as you go up? Anyways, as you're getting to these big buildings, the frequency of these structures, the dynamics of the movement of the structure starts really affecting the loading. You kind of talked about that vortice shedding. You start hitting this building with winds in different directions. I mean, all of a sudden you're going to start seeing all this weird stuff happen. So they went wind tunnel testing. They found a lot of things out about this building. Again, you want to learn more about it, check out our Instagram page. So what they ended up finding, just out of doing a little research, is they took a 3-story section, kind of, I think it was like floor 89-ish, took 3 floors, and they put louvers on all 4 sides and allowed the wind to go through the building in some manner. And they found that it drastically changed the pressure on the structure above and below that area, which, kind of makes sense. But when would you ever get the opportunity or understanding or time to see these kinds of things? I think it's so cool to see these massive structures and these really innovative things, because you can kind of apply them to a smaller level of structures. I mean, let's say something we deal with a lot, this is going a little tangent, it's like a screen wall. Well, shoot, you put some louvers on that, you let the wind go through. Maybe all of a sudden your screen wall supports don't have as much load and issue as you were having before.
Absolutely. And ASCE 716 does have a, what's the word they use? Basically a screen. So screen wall.
Exactly. Yeah, and an amount of open area, and then you can go from there. So I think that was really cool. And then so that significantly helped the loading on the building. It's a double core kind of buttressed system for the lateral. The other thing they found is there is an acceptable level of movement or vibration of the structure during a windstorm that will cause nausea. The peak lateral acceleration during the predicted sway of the tower has to be, and this was the limit they used, was 18 milli-G during a 10-year storm event. That is an industry standard on sway used for these big towers. Wow. And so to counteract that, the engineer decided to put in, drum roll please, but they put in these big water dampers. So cool. On those 3 stories where they had the louvers, they also put in water tanks. And then also on the roof, they put them there to dampen the structure while it's getting loaded. And so it helped in many ways, but the big driver to that was human comfort. They ended up adding 400,000 gallons of water to do this. Wow. And I imagine that's probably the fire proofing system as well, or fire suppressant system. I would assume they're using part of that as well. I think it's cool they came up with a solution to use 6 tuned liquid sloshing damper tanks. Like, what a mouthful. Yeah, I mean, performance design. We've said it, we've talked about it a lot, but that's the way things are going to go, and that's great. I think in the future, engineers are going to be a lot more driven to that understanding of performance-based design. I think it might take a while for like seismic design to get to lower structures. Right now it's really, really big in the skyscraper industry, which makes a lot of sense, because if you're just to go off code, those buildings would be solid concrete a lot of times. But the idea, like we talked about before with Patrick McManus during that interview, a little bit at the end about talking about ductility and performance-based wind design. I mean, that's just some cool stuff that's coming along. Okay. Yeah, man.
a good little tangent, but I think that's a good way to end and pretty neat. Thank you all for listening. Sorry, this one took a little while to get out. It was a hard one, honestly, but hopefully we covered it. If you have any questions or comments of your own, if you use exclusively the envelope procedure, please come and tell us now. See you later.
Have a good day.